So that's my second talk, and I hope that will be more interesting than the one of this morning. So this actually was the work of my thesis. So we're trying to develop innovative apolar gels based on cellulose derivative, in particular for the cleaning of metal artwork. What was the problem, as you heard this morning, for the protection of metal artwork that belong to cultural heritage? Hydrophobic and apolar protective coatings are applied. Thus, for their removal, we need an apolar solvent. But these, we all know, brings us some problems like emission of volatile organic compounds, non-sustainable production of the apolar solvent and their disposal process. And of course, health problems for the operators, so conservators that are cleaning the artworks. So the objective of the thesis was to try to gel this non-polar solvent in one of the most commoner thickeners that are actually used in cultural heritage sector, in particular in cellulose ether. And then once we were able to gel the non-polar solvent, the actual removal of these non-polar coatings, protective coatings from the outdoor and indoor metal artifacts. To do so, we first need to select which solvent to use, which thickeners between the cellulose ether we should use, and then since the solvent was apolar, while the thickener was polar, we needed something to bridge the two, so we needed an emulsifier. To choose the emulsifier, we start with the evaluation of the hydrophilic-lipophilic balance, and then we used the Hansen solubility parameters again by calculating the relative energy difference between the emulsifier and the solvent, and the emulsifier and the polar phase, which was the thickness. Once we selected all the materials of our formulation, we needed to optimize the formulation in terms of quantity of the emulsifying agent and the ratio of the solvent, so the apolar phase, and the thickeners, so the polar phase of our system. To select the solvent, we did a survey between different restorers of different age and formation, and we understand that Ligroin is the most used apolar solvent to remove this kind of hydrophobic coatings. Ligroin is a mixture of aromatic and aliphatic hydrocarbons, so it's a petroleum-based solvent. And since it's the most used, it became our reference solvent. Then in literature, we found for greener alternative, and in particular, we used methyl myristate and isopropyl palmitate. Then among all the different cellulose ether that we chose because they are biocompatible and for their thickening properties, there are a lot of different cellulose ethers to which one can choose from. So we use again the calculation of red to understand which one of them could be a good representation of all the different kinds of cellulose ether. And we come up with the crucial G, with the commercial name of an hydroxypropyl cellulose ether, which is currently used in conservation of cultural heritage by the restorers to thicken a water-based system. So we selected the solvent, we select the thickeners, we needed to select the emulsifier. There are so many surfactant and co-surfactant one can choose from. So we start by calculating which was the required HLB of our formulation for the different ratio of the solvent and the polar phase, which in our case was represented by our thickeners, so the clusal G, and the co-surfactant, which was the 1,2-hexanediol. Once we select the HLB, this brings us to 5 HLB values target. So we here I bring the representation of the calculation of the red in the Hansen solubility space. The one on the left is based on the Ligrain, the one on the right is based on the Clusial. So we evaluate which one of the surfactant we chose had the most chemical affinity to our components of the system. And then from all of them, we select the 5 within the 5 HLB target values. And these are the 5 we selected. So PEG 100, cetyl alcohol, a mix of twin 20 and span 80, mix them together to have a value of HP equal to 12. Then TFOS 63, which is already commercially available surfactant, and span 60. Then for the optimization, we start with a empirical scanning test, and in this test tube, by varying the percentage of the apolar, which is A, and the polar phase, which is P, from 100% to the other end of the scale. And as you can see, for example, in this case, we only obtain a clear and stable gel for this kind of percentage, so 25 apolar and 75 polar. And then once we macroscopically observe the stability, we use turbidimetry as an index to stability. And we find out that out of the 5 initial surfactants selected, PEG 100, span 60, and cetyl alcohol gave us the lowest value of turbidity, thus the more stable formulation. So we went forward with them, and we formulated 9 gel in total by varying the free solvent, so Ligrain, which was the reference, methyl myristate, and isopropyl palmitate, and using the 3 different kind of surfactants by keeping constant the thickener percentage of the glucose C and the co-surfactant, which was the 1,2-hexanediol. The formulation is pretty easy, so you basically just warm it up the solvent. Of course, we mind the temperature because we are working with an organic one. Then we add the surfactant and the co-surfactant. We cool the formulation around like 38 degrees Celsius or less, which is the solubility of Clusial G. And then we add actually the Clusial G to formulation. Once the solution reach the temperature, room temperatures, you have the gel. So we then characterize the gel in terms of stability, viscosity, and retention of the solvent, which are all parameters that are useful in conservation of cultural heritage application. Regarding the stability, we use a Turbiscan, which basically destabilizes the formulation over a period of time. And the higher the value of the TSI, the more unstable is the formulation. So as you can see, gel 6 and gel 9, after 10 minutes of the process, already show flocculation and destabilization of the gel. While the other all show pretty good stable performance over time, with gel-free being the more stable, so the one with the reference solvent and the span. Regarding the viscosity, we found a positive correlation between the HLB value and the viscosity. So surfactant with the HLB value higher gave us a higher viscosity of the gel overall. While the retention of the solvent within the gel was evaluated by thermogravimetric analysis, and we link the first weight percentage loss to the loss of solvent, while this second loss is related to the degradation of cellulose ether. And as you can see, gel 4 was the one that retained as a less, I know they were pretty kind of the same, by add the best, it lost its weight in a more gradual weight. Thus, we hypothesize that it has a more retention of the solvent. And then the fun part, we evaluate the cleaning effectiveness of the solvent first on laboratory mock-up. So I prepare oxidized frame, like you can find from a cultural heritage object, and we apply different kinds of coatings that are used in cultural heritage preservation. Then we age them because, of course, all the materials you will find on cultural heritage are pretty ancient, so they undergone aging process. And then we evaluate the cleaning effectiveness by multispectral imaging, digital optical microscopy, spectrocolorimetry, and infrared spectroscopy. Is you can this is an image that represents when you apply the gel on the surface of the frame. Multispectral imaging didn't show any kind of response of a different irradiation of the surface, so no surprise in that. Digital optical microscopy allows us to have a detailed observation of the surface. Like in this case, we could evaluate that the Reese wax, which is a wax, was removed from the surface, while the paraloid, which is a synthetic resin, which has a high refractive index, is still present on the surface. So our gel was selective in the removal of this coating. Spectrocolorimetry, we calculate the total color variation before and after the application of the gel. A value of 5 means a value lower than 5 means that no color perception is available to human naked eye. Regarding the residue presence, which is a interesting question in cultural heritage preservation, we did not find any peaks related to the solvent present or the cellulose ether. And then last but not least, we apply the gels on a real case scenario where, as you can see, before the application and after the application, the cleaning is actually pretty impressive. And just to summarize the result, Ligroin, which was the reference solvent, and SPAN 60 gave the better stability. The viscosity increased with the HLB value, and a more gradual mass loss suggests a potential slow release of the solvent. The cleaning test showed that the gels formulated with the reference solvent still have the best result, but that the greener alternative proposed were effective, but even if less consistent with the results. And in the real case study, the gels perform pretty well, and a combined use of the different gels has led to better results than the single use. Conclusion, the optimal formulation that gave the best overall result were made with cetyl alcohol. And the combined use of HLB and relative energy difference allow to a target selection of our surfactant. Future perspective, we are trying to actually vary the gelling agent to evaluate what was our first hypothesis, and of course use biosurfactant instead of the surfactant we are commercially used now. That's the paper you can find online with all the information regarding the research. And thank you very much for your kind attention.